Hello, everyone. Hello, can you all hear me? Okay, so I think we can start now. So, last section we have covered sets and subsets, and then intersection unions of sets. So the last session we have covered sets, subsets, and then some logic, including unions, intersections, and then I think we ended it with Cartesian products. So today I will start with functions. Today I will cover functions and relations. Functions and relations. So firstly, before discussing what a function is, we need to know what is what we say a rule of assignment. So a rule of assignment is a subset, let's say R, of a Cartesian product. C into D, these in big D. These two are any sets, C and D, such that if we have some C, D, some element of that Cartesian product, and then some element of that subset actually, and some another pair that has C and D prime, if this implies that D is equal to D prime, then this is what we say as rule of assignment. So basically the first item of this pair needs to be the same C. So that's what we call a rule of assignment. So now using this definition, We can also mention the domain of the rule of assignment, domain R. So this is the set of all such C such that there exists some D in this some element of D such that this pair would be in the subset R. So that's the domain. It's just the all values of this C of the first item in the pair, first element in this pair. And then we also have the image of this rule of assignment, which is the set of all D, so the set of all second elements. So you can also think of image as the range of function. If you have studied functions before, so image is also the range of function. So it's the same as above, except there exists some C such that CD is in this uh, subset R. So that's what our rule of assignment is. So now using this, we can define what a function is. So we denote a function. So our function is a rule of assignment. A function is a rule of assignment, or that is we denote this a function like this. So we have two sets in a function. This is called the domain, and this is called the codomain. So the domain is actually the domain of the rule of assignment. So the domain of function and the domain of the rule of assignment is the same thing. In the codomain, it's not actually the image set, but the image of the function is actually same as this. So it's let's say set of all small b such that now for this notation we can actually write, just a second. Wait. Okay, I'm back. So as I was saying, so the image of function is given by all such values, that is b is equal to fa. So now this thing, we call this the image of a under f. So it's essentially applying the function. So for at least one little a in the domain. So the image is of the function also sometimes called the range. So you can think of these two things as the same thing here. So now then we also have another thing of function that is called the pre-image. So we denote this by using this symbol, and we take pre-image of some subset of the domain of the function. We can also take the image of a subset usually, but let me first show how to take the image of a subset. So let's say we have some subset A0, of the domain. Then we can say if A0. So this notation you can see we are actually taking in a set here instead of an element like we usually do for normal functions. We are actually taking a set here. So this is actually the same definition almost, but you can just write it like this: the set of all if A such that A is in A0. So that's the image of this set under F, and then we have the pre-image, or inverse image. It's like the inverse function, but except we are working with a set. So when pre-image is like we want to reverse the image, we want to inverse it. Suppose we have this FA here, but we want to get just the A given the F we have, given the range we have. We want to find what input it was giving. So for this, we take a subset of the codomain. So we write it like this. So it's just the opposite thing. So we now get the set of all A. Now just to make sure that this is from the input domain, I'll write this. Actually, let me write this. It's clear that it's from the domain, this element A. So it's the set of all A such that f of A is in this set P0. So this is the pre-image of the function. Now we also have something what we call a restriction of a function, and we denote it by saying, let's say we have f some function a to b. Now we can restrict this function. Let's say we want to restrict this function to some subset of a, let's say C. So for example, this is A, the function's domain, and then this is the subset C. We want to restrict the function to just C. So we can use this notation here, use this vertical bar and C. So this function's rule is a bit different. We write it like this. And now notice that this A will be in this subset C. So essentially we just kind of cut down the domain and make it smaller into something more concentrated and focused. It's very useful sometimes. So that's the restriction. That's the restriction of the function. Now then we also have what we say a composite function. For example, I have some function f that maps from the domain A to B, and G that maps from B to, let's say, C. We can define the composite by saying G and then we put a circle F. Now this composite function, its domain is going to be A and the codomain will be C. So that's the composite function. For example, let's say I have a function F and that maps from real numbers to real numbers. So this is how we write a function that maps from real numbers to the real numbers. And then we use fx is equal to x squared. For example, this is our function f. And then we have other function g. Let's say this is 1 by x. So if we composite these two functions, we can write this as, so when compositing the functions, we read from right to left. So we start from here, then go here. So we first apply this function, then we apply this function g. First we apply f, then g, from right to left. And then, so in this case, first we apply f. So we write down x squared. Then we apply g on it. So by doing that, we can see it equals to, it's equal to 1 by x squared. So that's the composition. And you can also see the composition also has domain R and the codomain is also R. Some better example would be, let's say, if that maps from, let's say I take a natural number and also give a natural number, and I have G that takes a natural number but gives you a real number. For example, so let's say if it's defined like this, let's say f of n is equal to, let's say, n square, and g n square, no, let's just do n. Let's just say f of n is equal to n and g is equal to, let's say, square root n. So if we composite this function, let's say first we apply f, then we apply g. We cannot do the other way around. We can only do this because this will have the input from the natural number and the output from the real number. But if we composite g first, if we take g first then f, it won't work because g, in the codomain of g we have the real number, and in the domain of domain of f we only have the natural, so it won't work. This is not going to work here. So now the composition is just going to be gf in is equal to, so first we apply f, so we just have n, then we just put g over it, so that gives us square root n. So it's just the same thing. So that's example of composite functions. So there are various types of functions. We can now discuss the types of functions. So the first type of function is injective function. Which is also known as one-to-one. So an injective function is basically defined like say we have some function. Let's assume all the functions will be from this set A to B. Then say we have some if A and if B, for example. If A is equal to if B implies A equal B, then then we say the function is injective. So that's the injective function. So for example, we have, in case of injective functions, we have example. Consider just a real valued function. If x is equal to, just say, 2x, for example. Very simple example. Consider if A as something, for example, consider if A and if B. So if we have if A and if B, so that is 2A. So that means 2A and 2B. Say if A is equal to, let's say they are equal. Say these two are equal. Then we have 2A is equal to 2B. That implies by dividing both sides with 2, we are just left with A equal B. So this function is injective. This function is injective. So that's an example of an injective function. However, this function, if x equals to x squared, this is not injective, because consider if A, we can consider a counter example here. For example, consider if 2 and if minus 2. Do you agree these are two equal? Agree that these two functions are, these two values are equal, f of 2 and f of negative 2? What do you say, Chad? I think my volume's very low. Some people are saying we cannot hear me. Can y'all hear me? Okay. So this is 2 square is equal to negative 2 square. So 4 equals 4. So these two are equal. But 2 is not equal to negative 2. So this function is not injective. Not injective. but it is what we call surjective. So consider this example. So consider this definition: surjective function. We can just cheat and say a surjective function is any function that is not injective. That will work fine, but we need proper mathematical terms. So a function f is surjective. It's surjective if, let's say, we have some little b in the codomain. If this implies p equals to fa for at least one a in the domain. So let me give you an illustration of injective and surjective functions. Injective, surjective. So let's say this is the domain A and this is the domain B. We have some inputs here, some inputs A, B, C, D, and some outputs here, let's say X, Y, and Z. Okay, so for injective functions, you have some elements that only one output is affected by one input. So we have only one input to one output here, and not necessarily that all inputs should be mapped to some output. For example, this C here is not mapping to anything. So that's how injective functions are. But for surjective functions, so this A, B, C, D, A and B can map to the same output, and C can map to here, D can map to here. But all outputs will have something to respond with. Will have something in the domain that will map to it. So that's surjective. Example of surjective function is, for example, f equal x squared, and for injective we have, for example, linear functions like this, and then we have what we say a bijective function. A bijective function. So a bijective function is both injective and surjective. So that's what a bijective function is. A bijective function is also invertible. So an example of a bijective function is, let's say, fx is equal to x, just this, or 5x, 3x plus 2. This is bijective because it is both surjective and injective. You can check this if you want. For injective, it's very simple to show that this is injective, and then for surjective, you can just show that every element in this codomain will have the image. Actually, every element in the image will have at least will be actually non-empty. You can say that. they will have some input, some element in the domain that we map to it. That's what bijective, surjective, and injective functions are. So let's see what we got next. So we also have the inverse function. So this is not the pre-image here, but this is the inverse. So this inverse exists if only we have a bijection. So the example of a bijection is if we have four elements here and four elements here, all of this will map to some of them, but they won't map to the same thing. The inputs won't map to the same output, and it will all be distinct, and there won't be any things, any elements left out in the domain and the code. We have them all mapped. Unlike here, where elements can be mixed, in here elements can't be mixed. So that's injective, surjective, and bijective functions. So now I think we are ready to discuss relations. So a relation is a Cartesian product. Now, is a subset. A relation is a subset. Actually, we say a relation on a set S is a subset, let's say U of the Cartesian product. Actually, let's just write it here. Of the Cartesian product S times S. So, for example, let's say we have some x, y in this subset U, then we say x is in relation U. Let's just use R instead of U. It sounds much better. Is in relation R with Y. So that's what a relation is. So an example is consider this set of all x such that x, let's say collection of all x, y such that x square plus y square is equal to 25, for example. So this is a relation. This is a relation on this set. This is an example of a relation. So the relation is the x is the x coordinate lying on the circle, y is the y coordinate lying on the circle. So this is a relation here. Some very silly example of a relation. So the x and y are related because they both contribute to on this circle. So that's a relation. Now more intuitive example consider the set D. We can say this is the descendant relation. So it's the set of all xy pairs such that x is a descendant of y. So for example, if we consider son and father on this set, this is a relation because son is a descendant of father. So that's an example. So there are many kinds of relations. A function is also a special kind of relation. So now we can discuss what is an equivalence relation. An equivalence relation. So it's a relation R. Actually, we denote it with this symbol called the tilde symbol, such that it satisfies three properties. So first is reflexivity, that is A is in relation with itself for all A in the set A. Also, we mean to say equivalence relation on set A. And then we have the symmetry. A in relation with B implies B in relation with A for all A, B in the set. And then we have transitivity. So transitivity is basically A is in relation with B and B is in relation with C. This implies A is in relation with C for all ABC in the set. So that's what we say an equivalence relation. For example, the equality of real numbers denoted by equal. This is also an equivalent relation because firstly, let's say consider some number A. The number is equal to itself, so it satisfies symmetry. And then if we consider A and B, the real numbers A and B, if we have A equal B, then this also means that B is equal to A. Then we also have transitivity. If we have A equals B and B equals C, then we have A equals C. So that's an equivalence relation. Now there is something very helpful we have. Let's say we want to have a set of all equivalence relation. For example, we have some set A. Say we call this equivalence class of small a, which is an element of this. So the equivalence class is a subset of A, and it's basically equivalence class of this element. For example, A, we denote it like this. This is going to be a set of all numbers such that A is in relation with X. So that's the equivalence class. So A should have a equivalence relation with all the elements. So this makes a set. That's what we call an equivalence class. It's a set of all equivalence relations with respect to that element. Now there is a very helpful result we can actually use. So we call this a lemma. We have a very useful lemma that is two equivalence classes A and B are either equal or disjoint. So if we consider a simple diagram, we said this is the equivalence class of A and this is the equivalence class of B. They doesn't necessarily have to intersect, but for our proof we'll need it. So let's start by assuming that the intersection is non-empty, meaning they are not disjoint. So let's start by assuming this. Then we pick some random element. Let's say we just pick A here, A, and then we pick B here, and also in the intersection we have some element. Let's say this is C. Since this is an equivalence class, we can say pick A from here and then and okay, so then we have A is in relation with C. If we pick B from this equivalence relation, then we have B is in relation with C. Okay, so now by symmetry, B is in relation with C. This just means C is in relation with B. So from the first one, this implies that first, then we have A is in relation with C and C is in relation with B. Then by transitivity, A is in relation with B. So we have showed that if the intersection is non-empty, then A has an equivalence relation with B. But now we need to show that if we pick any element from A here, let's say some other element D, then it will also be in relation with B. That will show that they are just equivalence classes. So just for example, we just pick B, we just pick A or D, this from this, and then so that directly means D is in relation with A. D is in relation with A. I mean, A is in relation with D. A is in relation with D. Then by transitivity, once again, actually, I mean D is in relation with A. D is in relation with A. Okay, then by transitivity, again, we have D is in by transitivity, we have D is in relation with B. So that ends our proof. This means that if we pick any element, it will be in both the equivalence classes if the intersection is non-empty. So that should mean that both of these are equal. I hope that makes sense. So now that we prove for any element D of this equivalence class of A, we can now pick anything from B and the symmetry will just result in the same thing. So I won't go into that. You can check it yourself. By symmetry, the other next part of the proof is just trivial. So that ends our proof that two equivalence classes are either equal or disjoint. So now we are going to study a very important definition. We call this a partition. So a partition P of a set A is a collection of disjoint non-empty subsets of A whose union is A. So you can imagine of a partition as something like this. So let's say this is your set A, and you break this into many different sets. They don't intersect. These are non-empty sets. Let's say you break them apart. This is A1, A2, A3, A4, A5, A6. Doesn't matter if you're even or uneven. You just break them apart. So this is a partition. And if you take union of all of them, it will equal the set of set A. So that's what a partition is. So the next theorem we have is very important, which shows that the let's say we have an equivalence relation. So this is very important. It tells us that if we have an equivalence relation, then the set, the collection of all equivalence classes of A is a partition of A. So this is a very important theorem. We can also prove this similarly as we proved our previous one. So I won't go into the proof here. An outline of the proof is given in the book. You can try it yourself. And maybe I will post a video of the proof. So I'll move on now. But I want to say that the studying equivalence relations and partitions are the same thing. So the next thing we have are order relations. So this is denoted by this less than symbol. So these are almost like equivalence relation, but we have firstly the comparability. So for x every x and y in A, for which x is not equal to y, either x is less than y or y is less than x. Then we have the non-reflexivity. Non-reflexivity. So this just means x less than x is impossible for all x in A. Then we still have the transitivity. So x less than y and y less than z implies x less than z for all x, y, c in A. So that's an order relation. So I think the examples are very trivial of an order relation. That's an order relation. For example, if we consider 3 less than 4 on the real numbers, that's an order relation. Order relation. On R. So now using order relation, we can also define ordered sets. So let's first see what this notation means. This means notation. So this means, let's say we have x less than or equal to y. This means either x less than y or x equal to y. So that's what this notation means. So let's say we have some set A, which we have some order relation, on A. If we have some order relation on this set, on some set A, then and if we have some element and a subset, actually we need a subset, and the subset is 0 of A, then we say A0 is bounded above zero is bounded above if there is an P of A such that x is less than B for all x in A0. So basically, if we have a number that is greater than an element of B that satisfies this relation for all elements of this subset, then we say it's bounded above. Similarly, we say it's bounded below if let's say that B is greater than X for all X in A0. Or you can say, yeah, okay, B less than X for all X in A0. That's bounded below. So in here, B is upper bound. In here, B is lower bound. Smallest upper bound of all upper bounds is called least upper bound, or we also call it the supremum of the subset. So the least upper bound of the supremum. Similarly, the greatest lower bound is called infimum. Infimum. So that's the definition of ordered relation, supremum and infimum. Then we have what we call an ordered set. An ordered set is actually any set that has the ordered relation on it. So an ordered set is any set that has ordered relation on it. An ordered set A is said to have least upper bound property if every non-empty subset A0 of A that is bounded above has a least upper bound. So it's said to have the least upper bound property if every non-empty subset A0 of A that is bounded above has a least upper bound. So similarly, greatest lower bound property if it has greatest lower bound. So an example of this is, for example, we can consider the open interval. Let's say the open interval 0 to 2, and this is a subset of the real number, and this is equal to the set of all numbers between 0 and 2. So we denote the least upper bound by writing LUB, say LUB of 0 to 2, or we can also say sup of 0 to, this means the supremum. We can write any of them is 2. So this number is in the set, is in the real. So this is the least upper bound for this specific set. Similarly, the greatest lower bound for this set is 0. So it's kind of like that. So not all sets actually have the least upper bound property. For example, if we consider um, okay, so for example, we have this set that is the union of two open intervals. We have said this that is the union of two intervals. So this set does not have the least upper bound property because we have some missing. Actually, we have some elements missing here. For example, we don't have 0 here. So if we consider, for example, 1 as the consider 1, let's say you are saying that this set is bounded above by 1. Consider 1. If you say it's bounded above by 1, then you'd be wrong, because for every element, actually, it does not have this upper bound, because how to say it, Yeah, so this set basically doesn't have a least upper bound because it's bounded above by one, but because there's kind of a hole here. Let me show. This interval is bounded above by one, but if you consider the union of these two, then if you consider just the subset of this, because least upper bound needs to be the number that bounds above all of the numbers here. So just in the first interval, we really cannot have a least upper bound for this one, because if we were to have a least upper bound here, we don't have one in this set, neither in the next set. Like in between, we don't have one. So this set does not have the least upper bound property. However, this open interval, this has the least upper bound one. So yeah, I think that's it for today. We have covered uh, functions relations. We covered the rule of assignment, the function, image, pre-image, composition, the types of functions, injective, subjective, bijective, and relation. We also covered equivalence relation, equivalence class, and this lemma that two equivalence classes are either equal or different. And we covered the partition, and then we stated a theorem about the equivalence set of all equivalence class and the partitions being the same thing, order relations, and then we covered bounded above, bounded below, the least upper bound, supremum, infimum, and order sets having least upper bound property and greatest lower bound property. And I think that's it for today. Thank you for being here to the end.
Okay, so I guess that's the end of it. All right, thank you all for joining today. All right, have a good day.